Hi there. So in this video, we will look at intermolecular forces. So far, we have talked about intramolecular forces. Intra means within. And these are forces that act within a molecule. So for example, ionic, covalent, and metallic bonding. Intermolecular force, inter means between. These are forces that act between stable molecules. And differences in physical properties are the direct result of intermolecular forces. They are also called van der Waals forces or interactions. So we're going to look at three types. The first type we're going to look at are dipole-dipole. These are attractions between opposite charges in polar molecules. They're relatively strong, and they occur between all polar molecules. The more polar a substance is, the stronger the dipole-dipole force. So here are a couple of examples from your textbook. We have hydrogen chloride, two molecules of hydrogen chloride. The bond is the intramolecular force, and this little dotted line here is the intermolecular force between the molecules. It's dotted because it's not as strong as a bond, but the positive end of the hydrogen and the negative end of the chloride will cause them to interact together and attract. So it changes properties of substances. It has an impact. Okay, hydrogen bromide's another example. We could draw this like this as well to simplify it. So have a little dotted line would be the intermolecular force, and that would attract to the next hydrogen. It's what makes the hydrogen chloride stick together. And I'll shorten intermolecular force to IMF, intermolecular force. So these occur in polar molecules only, not in nonpolar. But London dispersion forces, the next type, is a weak attractive force in all entities. Between all entities, including nonpolar molecules and unbonded electrons caused by the temporary imbalance of electrons within entities. So in an entity, electrons will sometimes spend a bit more time in one location to another, which will cause an imbalance of electrons and cause it to attract to another entity that's close by where it also has an imbalance. So let's say it's a little bit more positive and they'll interact together. So the more electrons an entity has, the greater the London dispersion force. And it's very weak. I just noticed this little sentence here is missing in your package. So just don't worry, you don't need to write that. I'll move that up a little bit. Okay, so dipole in polar molecules, London dispersion in all molecules. So this little chart here is showing you a comparison of physical properties for several nonpolar substances. So if we look at, it's explaining, you know, how many electrons they have and how the London dispersion forces increases in strength. So helium, for example, has 2 electrons. Hydrogen has 2 electrons per molecule. Argon has 18. That's if you look at the element argon. Chlorine has 34 as a molecule. Bromine has 70, and sulfur has, that's an 8. That is an 8. That's how sulfur exists. It has 128. So the more electrons, the more imbalance there'll be. And this is the imbalance I was talking about. So sometimes you'll see there'll be one end will be slightly positive, another will be slightly negative, and these are the London dispersion forces in between. There's like an attraction sometimes and a repulsion other times. So the negatives are repulsing, the positive negatives are attracting. Lots of interactions. Positive and positive will repulse, the negatives will repulse here. So lots of interactions happening, and it occurs in all substances. And it also accounts for why some substances are gases at room temperature. There's those weak forces between the molecules. It exists in all molecules, even polar molecules, but of course London dispersion are insignificant compared to dipole-dipole. I'll show you a little scale at the end of comparison. And it only happens when the molecules are close together. Okay, so this is figure 7. It says see figure 7. That's what we were just looking at before. Hydrogen bonding is the third type. It is the strongest one. Okay, and it's a type of dipole-dipole because it's occurring in a polar molecule, right? But it only occurs with nitrogen, oxygen, and fluorine that are bonded to hydrogen. So hydrogen and oxygen, hydrogen and nitrogen, hydrogen and fluorine. Why? Because this oxygen is so going to have so much negative charge and getting close to this hydrogen, which is really tiny and positively charged. It's a very strong attraction, okay? Much stronger than dipole-dipole because of the difference in electronegativity, right? So here we have 2 hydrogen fluorines that are close by, and we have, even call it bonding because that's how strong it is, although it's not a bond so much as a force, but because of this, they want to, you know, emphasize the strength of it, they call it a hydrogen bond. So this explains what I just said. We've got a couple more examples here. We've got hydrogen bonding between hydrogen and oxygen, so water, hydrogen and nitrogen, and hydrogen and fluorine. So the bonds are occurring between the oxygen of one side and then the hydrogen. So it's always oxygen, nitrogen, or fluorine bonded to hydrogen. So why do these hydrogen bonds occur? Because of the large differences in electronegativities, as I mentioned, and the small size of the hydrogen atom, which means that the positive pole is highly concentrated and strongly attracts the negative pole of the nearby molecule. Why are these important? Well, we wouldn't have DNA without it. Very important in DNA and in proteins. So parts of enzymes, hormones, and antibodies. Cool biology stuff you probably learned about. Okay, so here is part of a DNA molecule. You can see the hydrogen bonding that's occurring between, here we have oxygen and nitrogen. So hydrogen bonding that's occurring in this. Oh, and down here we have another oxygen hydrogen bond. So hydrogen bonding is what allows, it forms between the hydrogen, oxygen, or nitrogen atoms in a DNA molecule. And we're not seeing the carbons. This is a special kind of structure that does not show the carbons, but wherever you see two things joined up, so for example here, this would be a carbon. Carbon, carbon. Okay, so wherever you don't, carbon, carbon, wherever there are joins between the bonds, there's got to be something there. So that would be like nitrogen goes to carbon, and then we got a double bond there, another carbon like this, and carbon will be on this side too. So I was just kind of drawing this little part here. Okay, so nothing to worry about in terms of that, just trying to explain why there's so many little lines there. Maybe you've never seen that kind of structure. Okay, so summary of the intermolecular forces. Oh, here it is. So we have, how do you determine what kind of forces are present? And that's the whole goal of this lesson. How do you determine what the forces are and the strengths? So that's what we're learning here. So we look at the interacting molecules and we say, are polar molecules involved? If the answer is no, we go straight over here. We only have London forces. Okay, so that could be some examples. There's just argon or iodine. And these are weak intermolecular forces relatively, and they have relatively low melting and boiling points. So this is an important chart to remember. I know it looks slightly different on your page, but you've got the same thing there. Okay, then if they are polar, we have to look and ask the question, are hydrogen atoms bonded to nitrogen, oxygen, or fluorine? The answer is no. Then it's dipole-dipole forces. And London, you can't forget that those are there too. So if you're asked, you have to name both. So examples would be hydrogen sulfide and CH3Cl. And these are medium strength intermolecular forces. They have intermediate melting and boiling points. And then lastly, if we have hydrogen atom bonded to nitrogen, oxygen, or fluorine, then we have hydrogen bonding and London forces. So examples would be water, ammonia, or hydrogen fluoride. And these are strong intermolecular forces, and they have high melting and boiling points. This little chart here shows you the relative strength of intermolecular forces. So check this out. This is bonding. Okay, so ionic and covalent bonds are way up here at 100. Hydrogen bonds are here. Like, I mean, if this was about 50, let's say that's 25. Let's say this is 10. So this is less than a 10 for hydrogen bonds. Dipole-dipole looks like it'd be about a 5. And then London dispersion looks maybe about a 1 in terms of relative strength. Okay? So those are intermolecular forces, and they affect the properties of substances just like bonding does. Now the homework, do not do the homework here. Make sure you look to your package to determine what homework you need to do.